Hello everyone. Myself Piyusha Shetgar, Assistant Professor, Walchand Institute of Technology, Solapur. Today in this session we'll see the problem on differentiator. This is the learning outcome for today's session. At the end of this session, students will be able to design a differentiator circuit using Opamp. Initially we'll see the differentiator circuit, and after that we'll solve the problem on differentiator by using Opamp. Before going to start today's session, you can pause video here and recall that what is an inverting amplifier and what is the voltage gain for the inverting amplifier. Yes, in an inverting amplifier, input is applied to inverting terminal while non-inverting terminal is grounded. For inverting amplifier, closed loop voltage gain is given by AF equal to minus RF by R1, where R1 is connected at the input side and RF is the feedback resistor for the inverting amplifier. Now let us move on the differentiator circuit. This is the circuit diagram for practical differentiator. What is differentiator? As the name suggests, the circuit performs the mathematical operation of the differentiation. That means the output voltage is the differentiation of the input voltage. Here the output waveform is nothing but the derivation of the input waveform. So this is the circuit diagram for the practical differentiator. At the input side, the combination of RC network is connected, whereas in the feedback circuit also the RC network is connected for the practical differentiator. Now let us check the waveforms obtained for the differentiator circuit. You can apply input as a sine wave as well as the square wave, and let us check the output for the differentiator circuit. We know that the output is the differentiation of the input signal. Suppose the input signal is the sinusoidal signal as shown in this figure with the peak to peak value is given. After that you are getting the output is the differentiation of the input signal. That means output is the cosine of the input signal as the input signal is the sine wave. Now if the input signal is the square wave, output signal for the differentiator circuit is the spike wave. Now what is the frequency response of a differentiator circuit? Let us move towards the frequency response. What is the frequency response? There is the variation of the frequency, then we are getting the variation in the gain of the Opamp circuit. So this frequency response shows the gain in decibel versus the frequency of the differentiator. So here as you go on increasing the frequency, the gain also start to increases. The gain will start to increases with this dashed line is shown for the ideal differentiator. The gain increases at the rate of 20 dB per decade. But for the practical differentiator, there is some limit for the gain. So at this point, the gain will start to decrease for the practical differentiator at the rate of minus 20 dB per decade. So here you are observing the two frequencies F1 and F2. In some of the cases, it is defined as FA and FB. So F1 or FA is the frequency where you are getting the gain is 0 decibel, and F2 or FB is nothing but this point where the gain start to decrease as the frequency increases. Therefore, this frequency is also known as gain limiting frequency. Thus, you can define the two frequencies for the differentiator circuit. The frequency at which the gain is 0 decibel and is given by FA equal to 1 upon 2 pi RF C1. And the gain limiting frequency FB is given by FB equal to 1 upon 2 pi R1 C1. These are the two frequencies considered while designing the differentiator circuit. Now let us move towards the design problem for the differentiator. So design statement is given. Design an Opamp differentiator that will differentiate an input signal with the maximum frequency value is equal to 100 Hz is given. Draw the output waveform for a sine wave of 1 volt peak at 100 Hz applied to the differentiator circuit. And the third point is given that when the sine wave is replaced by the square wave, what will be the output for it. Now let us check the solution for this problem. So according to the design consideration, first select that whatever is the given frequency is nothing but the frequency at which the gain equal to 0. So the FA equal to max frequency equal to 100 Hz. As we know that FA is given by 1 upon 2 pi RF C1. Now FA is given which is equal to 100 Hz. So let us select the value for the capacitor equal to 0.1 microfarad. Then C1 is known, FA is also known. You can find out the value for the RF. Thus RF equal to 1 upon 2 pi FA C1. So from that value you can calculate the RF by putting the values of C1 and FA. So 1 upon 2 pi FA equal to 100 Hz given, whereas the C1 equal to 0.1 microfarad. So by solving this equation, you are getting the value for the feedback resistor equal to 15.9 kilo ohm. Now consider the FB value which is always greater than the FA. So let us choose that FB is equal to 10 times of the FA value, where FA equal to 100 Hz. So 10 times of 100 Hz, you are getting this equal to 1 kilohertz. Now we know the formula for the FB frequency, which is nothing but used for the gain limiting purpose. So FB equal to 1 upon 2 pi R1 C1. Now we know the value of C1 and FB. FB equal to 1 kilohertz and C1 equal to 0.1 microfarad. So by putting these value, you are getting the value for the R1 resistor. So here R1 equal to 1.59 kilo ohm. Now RF and R1 both are calculated. Now there is need to calculate the CF feedback capacitor. So now you know the relation of RF CF and R1 C1, which is nothing but RF CF equal to R1 C1. So this gives the time constant, which is generally we are taking the equal values. So CF equal to R1 C1 upon RF. So R1 equal to 1.59 kilo ohm and C1 equal to 0.1 microfarad upon RF equal to 15.9 kilo ohm. So by putting these values, we can find out the value for the feedback resistor. So by putting these values, you are getting the value for CF feedback capacitor equal to 0.01 microfarad. Now by using these all formulae, you can draw the circuit diagram once again with these values. Now let us check the output waveform when the sine wave of 1 volt peak is applied at 100 Hz as an input signal for the differentiator circuit. So we know the equation for the output voltage for the differentiator circuit, which is equal to minus RF C1 d by dt of Vi, where Vi is nothing but the input signal. Minus sign as it is, RF equal to 15.9 kilo ohm and C1 equal to 0.1 microfarad. D by dt of the input signal, that means you are taking the differentiation of the input signal for differentiator circuit. Now Vi 1 volt peak value is given for the input signal. So by putting that 1 volt here, as we know that sinusoidal signal which having the equation equal to Vm sin omega t, where omega is the angular frequency, can be written as 2 pi f, where f is the frequency which is given equal to 100 Hz. So Vm is the 1 volt, sine of omega is 2 pi f. So 2 pi f is the frequency, that is 100, and t. Now differentiate this value. So differentiation of this sinusoidal signal is equal to minus 15.9 kilo ohm, 0.1 microfarad, 2 pi 10 raised to 2 cos of 2 pi 10 raised to 2 t. Now by solving this, you are getting the V out equal to minus 0.999 cos of 2 pi 10 raised to 2 t. So 0.99 means nearly equal to 1. So output also having the amplitude equal to 1 only. So minus 1 cos of 2 pi 10 raised to 2 t. So this equation shows that it is the wave which having the minus 1 is the amplitude initially, and which is shifted by this phase angle. Therefore, for the sine wave output, you are getting the cosine wave with the 10 millisecond is the time period for it. So here if you observe the input and output waveform, here the input is the sinusoidal signal, whereas the output is the cosine of the input signal with the same amplitude, and the time limit is equal to 10 millisecond. Now let us consider it for the square wave. Again you can use the same equation, V out equal to minus RFC1 d by dt of the Vi. So by putting all these values, you are getting the same equation, V out equal to minus 1 cos 2 pi 10 raised to 2 t. Now let us draw the output waveform. If the input is equal to square wave, the input is having the 1 volt is the peak value, thus 2 volt peak to peak value is applied as a square wave. So for the square wave, differentiator circuit gives the spikes as a output signal for the square wave as the input for differentiator circuit. These are the references used for today's session. Thank you.